Hi, everybody. Welcome back to the second week of Physics Computer Science 219A, Quantum Computing. I hope you're all well. I hope you're all getting into the swing as the academic year wraps up. In this, the third lecture of the course, we're going to continue with our discussion of density operators and also discuss a generalized notion of measurement. So let's get to that now. So this is really the second of a sequence of lectures in which we will be developing the theory of open quantum systems. And you'll remember that we say a system is open if it can exchange energy and information with its environment, where we're not monitoring the environment. Last time we talked about how to discuss states of an open system. Those are described by density operators, that is, non-negative Hermitian operators with trace 1. And we also discussed the idea of a Schmidt decomposition of a bipartite pure state. Now today I want to talk about measurements that are more general than the orthogonal measurements that were specified when we formulated the axioms for closed systems. These are measurements that can be realized when a system interacts with an auxiliary system, and then an orthogonal measurement is performed on that auxiliary system. And the result of that is something more general than applying an orthogonal measurement to the system itself. But before we get into that, we're going to continue the discussion of density operators for a little while and get to some additional concepts that we didn't get a chance to cover in the previous lecture. So we'll be continuing with material in chapter 2 of our notes and then onward to the discussion of measurement in chapter 3. I'd also like to point out that the first homework of the course has now been posted. There's a link to it on the course website, and the homework is going to be due a week from Friday on October 16th, and we will have instructions on Canvas and Piazza about the process for submitting your homework and having it returned to you. So let's remember what we said last time about the idea of a density operator. We can imagine splitting the universe into two parts, a system A under Alice's control, and we're interested in what kind of observations Alice can make when she looks at system A. But there's actually a joint pure state for the closed system consisting of Alice and her environment, which we're imagining is under the control of another party, Bob. So there is some bipartite pure state, which I can expand in terms of an orthonormal basis for Alice's system and Bob's system. But if we want to consider any measurement that can be done on Alice's system alone for the purpose of assigning probabilities to the measurement outcomes, we don't need the full bipartite state. All we need is the density operator for Alice's system, which is obtained by performing a partial trace over Bob's system. And in terms of an orthonormal basis for Alice's system, that can then be expressed as I'm showing here in the expression for rho A, given that the joint system is this bipartite pure state expanded in terms of complex coefficients and an orthonormal basis. And we observe that a density operator obtained in this way has three fundamental properties: that it is, first of all, a Hermitian operator. It is also a non-negative operator, Hermitian with real eigenvalues, which are non-negative real numbers. And the density operator has trace 1. That corresponds to the feature that if we perform any measurement on Alice's system and assign probabilities to the outcomes, those probabilities have to sum up to 1 because some outcome occurs each time a measurement is performed. We also noted that because it's a Hermitian operator, there is a basis in which the density operator is diagonal, and the eigenvalues of the density operator, the coefficients of projectors onto those orthonormal basis states of the density operator, can be interpreted as probabilities. They are non-negative real numbers such that the sum of all of the PIs is equal to 1. And in fact, we can give a nice interpretation to the density operator. We can imagine that someone has prepared a state of Alice's system in the following way, that the state is prepared in one of those orthonormal basis states, in the basis that diagonalizes the density operator, and that Alice consults some source of random numbers, and by doing so, she samples from a probability distribution, and with probability p sub I, prepares the orthonormal basis state I. And although that might not really be how the state was prepared, for any practical purpose of interest to Alice, for any measurement that she performs, she can tell the difference between making a measurement on a state prepared in that way and making a measurement on Alice's half of this bipartite pure state, which has the specified density operator. Another thing we talked about was a particular basis in which a bipartite pure state of systems A and B has a special form. This is called the Schmidt basis, and that special form of the bipartite pure state is called the Schmidt decomposition. What we do is we use the basis in which Alice's density operator is diagonal to express the state in terms of a basis for Alice's system, and also the basis in which Bob's density operator is diagonal, obtained by doing the partial trace over Alice. And then the bipartite pure state has this simple form. It's a sum over a single index, the square root of a probability, an eigenvalue of the density operator, orthonormal state I for Alice, and what I call I prime, one of the orthonormal basis states for Bob. So the basis elements are paired up in this way in the bipartite state. Once we've chosen that Schmidt basis, or the basis in which the density operator is diagonal for both systems. And one way of thinking about how we arrive at the Schmidt form is if we look back at the bipartite pure state in its general form here in terms of some general orthonormal basis for Alice's system and Bob's, this matrix AI mu, in general a rectangular matrix because Alice's and Bob's systems might have different dimensions, can, like any rectangular matrix, be expressed in terms of a singular value decomposition. If we have the freedom to make a unitary change of basis for the first index and another independent unitary change of basis for the second index, we can put that matrix into a diagonal form with non-negative coefficients. That's the singular value decomposition of the matrix. And by choosing those bases that put a matrix in that singular value form, we can perform the Schmidt decomposition, or put that bipartite pure state into the Schmidt form. And we can see from the Schmidt form one consequence, which is that when we do the partial trace over Bob's system, we get probabilities p sub I. Those are the eigenvalues of Alice's density operator. But if we perform the partial trace over Alice's system to get Bob's density operator, we get a density operator which has the same eigenvalues. So the non-zero eigenvalues of Alice's density operator and Bob's, if they share a bipartite pure state, are always the same. Because the dimensions of the two systems might be different, the number of zero eigenvalues might be different for Alice's system and Bob's, but the non-zero eigenvalues are guaranteed to be the same. Now, there's a kind of geometrical property of density operators, which is useful to know. We can think of the density operators as living in a a linear space, we can imagine taking linear combinations of density operators, and the space of possible density operators or density matrices of some specified finite dimension is a convex space. And what that means is that if I have two density operators, let's say rho 1 and rho 2, and then I consider taking the sum for some real number between 0 and 1, lambda, lambda rho 1 plus 1 minus lambda rho 2, let's call that linear combination rho of lambda, that also is a density operator. Remember, by a density operator, we mean an operator which is Hermitian and has non-negative eigenvalues and has unit trace. Well, it's actually obvious that if rho 1 and rho 2 are both Hermitian, then this linear combination is also Hermitian because lambda and 1 minus lambda are real numbers equal to their complex conjugates. It's also obvious that the trace will be 1 for rho of lambda if the trace of rho 1 is 1 and the trace of rho 2 is 1, because the trace of rho of lambda is just lambda times the trace of rho 1 plus 1 minus lambda times the trace of rho 2. Now we should also ask whether rho of lambda is a non-negative operator. I've said positive, but when I say positive, sometimes I really mean non-negative. What I mean is it doesn't have any negative eigenvalues, or in other words, if I take the expectation value, the diagonal matrix element of rho of lambda in any pure state, then the result has to be a non-negative real number. Well, what we can see is that if we substitute in the expression for rho of lambda in this matrix element between psi on the right and psi on the left, the result will be lambda times the expectation value of rho 1 plus 1 minus lambda times the expectation value of rho 2. And because rho 1 is non-negative and rho 2 is non-negative, and because lambda and 1 minus lambda are non-negative, this is a sum of non-negative numbers and therefore has to be greater than or equal to 0. So rho of lambda is indeed a density operator. Now rho of lambda has a nice interpretation because we can imagine that there's some party, Charlie, who is preparing a state of Alice's system, and he does it in the following way. He's going to prepare for Alice either the state rho 1, the state described by density operator rho 1, or the state rho 2, and he's going to do so with assigned probabilities, numbers lambda and 1 minus lambda, that sum to 1. So he flips some coins, he consults some randomness, he samples from a distribution, and with probability lambda, he prepares rho 1, or with probability 1 minus lambda, he prepares rho 2. And the state prepared that way is certainly a possible physical state of the system. There's nothing wrong with Charlie consulting some randomness to decide whether to prepare rho 1 or rho 2. But there isn't any way that Alice can tell the difference between a state described by the density operator rho of lambda or a state which was either prepared as rho 1 with probability lambda or rho 2 with probability 1 minus lambda. For any observable that Alice might want to measure, we can consider the expectation value, including both the expectation value with respect to that distribution that Charlie consults, and with respect to the expectation value in Hilbert space of the density operator, whatever it be, rho 1 or rho 2. And then with probability lambda, Charlie has prepared rho 1, and then the corresponding conditional probability or conditional expectation value of m would be the trace of rho 1m. With probability 1 minus lambda, Charlie has prepared rho 2, and conditioned on that preparation, the expectation value of m would be the trace of rho 2m. So altogether, the expectation value of m is just the trace of rho of lambda m. So this preparation that Charlie carried out by consulting a source of randomness is really just a way of preparing the state, which we called rho of lambda. So geometrically, we can think of the space of possible density operators and the space of all possible D by D matrices, if we're considering a D-dimensional system, as a convex space in the following sense. I consider any allowed density operator rho 1 and any allowed density operator rho 2, and then I can consider a straight line connecting those 2 points, defined as I defined rho of lambda here, and every point along that line with the 2 endpoints, rho 1 and rho 2, is a possible density operator of the system. That's a property of a convex space. Now, if you're given a mixed state, there are actually lots of possible ways to prepare that state by sampling from an ensemble. And we can kind of see that from this geometrical picture. If we pick out some point in the interior of the set of all possible density operators in our space of D by D matrices, then consider the point that I'm pointing to here with my red laser. That can be expressed, that is, it contained on many different line segments that go through that point. And for each one of those segments, I can imagine preparing this state as a convex combination of, say, these 2 states. So if this is rho 1 and rho 2, by choosing the appropriate weights, I can prepare a state which lies anywhere along that line segment connecting the 2 blue dots, and with the appropriate choice of lambda, I hit this point here. But I could also choose 2 other points in the set of possible density operators and draw a segment connecting them that goes through that same point. And so that's a different preparation as an ensemble of 2 different density operators with appropriately assigned probabilities that gives me exactly the same density operator. From the geometrical picture, we can see there are lots of preparations of a particular state as convex combinations of 2 or more density operators. But there's an exception. The pure states don't have that property. The pure states are what we call extremal, meaning a pure state density operator cannot be obtained as a convex combination of 2 other density operators. Well, let's see why that's true. So suppose I have some pure state here. It's just the projection onto some state vector psi. And suppose I could write it as a convex combination of some rho 1 and some rho 2. Now, for any vector in Hilbert space, psi, let me consider any vector I please, which is orthogonal to psi. I called it psi perp. It has the property that the inner product of psi perp with psi is equal to 0. So now let's consider the matrix element of rho, which in this case is this pure state, between psi perp on the left and psi perp on the right. Well, obviously that's 0, because I just get the inner product squared of psi perp with psi, and because psi perp and psi are orthogonal, that's 0. Now, if rho can actually be written in this as this convex combination, then 0 will also be equal to lambda times the expectation value of rho 1 in the state psi perp, plus 1 minus lambda times the expectation value of rho 2 in the state psi perp. But that means that 0 is a linear combination of R0. And if lambda is not equal to 0 or 1, that means that for both rho 1 and rho 2, the expectation value in psi perp of rho 1 and the expectation value in psi perp of rho 2 is equal to 0. But remember, I could have chosen psi perp to be any vector which is orthogonal to psi. And the only way that rho 1 or rho 2 could have the property that the expectation value for any such psi perp is equal to 0 would be for rho 1 or rho 2 to be the pure state psi, to be the projection onto psi, okay? So that means that our attempt to construct the pure state as a convex combination of 2 other density operators has failed, okay? So that's why we call it an extremal state. That's what's pure about a pure state. It can't be obtained as a convex combination of two other density operators. It can't be obtained by consulting some random source, some probability distribution, and preparing either row 1 or row 2. Now, we talked before about the pure states of a qubit, but now I'd like to talk about mixed states of a qubit. What is the most possible density operator for a qubit for a two-dimensional quantum system, a quantum system whose Hilbert space is two-dimensional? Well, a density operator, in this case, is a 2x2 matrix, which is Hermitian and non-negative, and has trace 1. So here I've written down the most general form for a 2x2 matrix which has trace 1 and is Hermitian. That's a space of matrices which is three-dimensional. It's described by 3 real parameters. The off-diagonal elements, of this matrix are complex conjugates of one another because rho is orthogonal, and the on-diagonal elements, the 0, 0, and 1, 1 element, have to have a sum of 1 because this matrix has trace 1. So it was convenient to pull out a factor of 1/2 and to write that in terms of the real parameters P3, P1, and P2. So now, this is a 2x2 matrix, which is Hermitian and has unit trace, but we have to check that it's non-negative, that it doesn't have any negative eigenvalues. Well, since it's just 2x2, and because its determinant is the product of its two eigenvalues, being non-negative means having a non-negative determinant. Because it has trace 1, if one of the eigenvalues is negative, the other one has to be positive, and the product of the two would be negative. Now, it's easy to evaluate the determinant of a 2x2 matrix, and in this case, we get a factor of 1/2 squared that I can factor out, and the product of the 0, 0, and 1, 1 components of this matrix is a 1 minus P3 squared, and then minus the product of the 0, 1, and 1, 0 components of the matrix. That means minus P1 squared minus P2 squared. So I can write the determinant of rho as 1 minus the length squared of a vector whose components in a three-dimensional real space are P1, P2, and P3. And for a non-negative density operator, that's got to be non-negative, which means that the length of this vector has to be less than or equal to 1. If it's less than 1, then the determinant is non-zero, and that means that there are two non-vanishing real positive eigenvalues, and if it's equal to 1, then the determinant is 0. And that's the case of a pure state, where one of the eigenvalues is 1, and the other eigenvalue is 0. So if we want to think about density operators of a qubit in geometrical terms, we can envision a ball in a three-dimensional real space where the coordinates in that space are P1, P2, and P3. We can draw a sphere where the radius is 1, that the length of the vector P is equal to 1, and those are the pure states. We talked about those before. We talked about the pure states of a qubit being in correspondence to points on a two-dimensional sphere. But in the case of mixed states, we can imagine filling in that sphere, filling in its interior, and all the points in the interior are possible density operators for our two-dimensional system. So the space of states of density operators for a qubit is called the Bloch sphere. Bloch was person, Felix Bloch, that it's named after. And it's really not such a great idea to call it a sphere because it's really a ball. It includes the points which are in the interior of the sphere, but people often speak of the Bloch sphere with either pure states, which really are on a sphere, or mixed states, which are in the interior of the ball in mind. Well, as I said, the boundary of this Bloch ball really is a sphere, That's when the determinant is equal to 0. That's when the state is pure. And that's what we already discussed in the previous lecture. We talked about the possible pure states of a qubit being in one-to-one correspondence with points on a two-dimensional sphere. We can recover what we said then in the following way. So the density operator for a pure state, that's the case in which the length of the vector p is equal to 1. In other words, it's a unit vector. So that becomes 1/2 times identity plus n hat, a unit vector, dot sigma. And a property you can easily check, and I think we talked about last time, is that you take n hat dot sigma for any unit vector n hat, and remember by vector sigma, I mean the Pauli operators, sigma 1, sigma 2, and sigma 3. And no matter what n hat is, if you square that operator, you get the identity. So in other words, its eigenvalues are +1 or -1. So that corresponds to if you measure n hat dot sigma for a qubit, you will get outcomes which are either +1 or -1. Now, since n hat dot sigma squared is equal to 1, we can see the following thing, that if I multiply this density operator row of n hat on the left by n hat dot sigma, well, then I get n hat dot sigma plus its square here, which is the identity. That, in other words, I just get rho back again. And likewise, if I multiply row of n hat by n hat dot sigma on the right, I just get rho back again. So in other words, what that means is that rho of n hat is just the pure state of a qubit that we talked about last time. I labeled n hat using the using polar angles, theta and phi. And remember, the pure states could be written as state vectors of the form that I called psi of theta and phi, and the density operator is just the projection onto that state vector. Now, another thing that's good to know about these Pauli operators is that if I consider I and j to vary over 1, 2, and 3, the three Pauli operators, sigma 1, sigma 2, sigma 3. Actually, let me come back for a second because I didn't say this clearly enough. If I go back to my form row of p hat, you can see that what I've written here after I factor out the 1/2 is p3 times the diagonal matrix with eigenvalues 1 and -1, and that's just p3 times sigma 3. And then remember that sigma 1 had entries 1 in the upper right and lower left. So here I also have p1 times sigma 1, and that sigma 2 had entries -I and I off the diagonal. So this contribution is just p2 times sigma 2. And so that's why I was able to write this as identity, that's the diagonal part, a 1 in the upper left and in the lower right, plus vector p dotted with a sigma, that is p1 sigma 1 plus p2 sigma 2 plus p3 sigma 3. Now, another nice thing to know about these sigma matrices is that if I take the trace of sigma I sigma j, where I and j run over 1, 2, and 3, that trace vanishes unless I is equal to j. If I is equal to j, then the product is the identity, which has trace 2. So I can write the trace of sigma I sigma j as 2 delta ij, the Kronecker delta. Now, if I'm interested in the density operator described by p, that is this row of p, in that state, if I'm interested in the expectation value of n hat dot sigma, the expectation value, the average value of n hat dot sigma, if I measure it many times, that is the trace of the density operator times that observable. So let's just expand that out. I can write the n hat dot sigma as the sum over I, and I sigma I. I can write the p dot sigma as the sum over j, pj sigma j. When I take the trace, only the terms with I equals j survive. I get a 2 here in front of the delta ij, which cancels the 1/2, in the normalization of the density operator. So what we're left with is just the sum of ni pi. It's just the dot product of that unit vector n and the vector p, which we use to label the density operator. So that's the expectation value of the spin along the n-axis of in the state described by the vector p. We call p the polarization of the qubit. It tells me what direction to choose to measure in order to maximize that expectation value. And when the polarization is actually a vector which has unit length, those are the pure states, so that if I choose the right axis, I'll have an expectation value of 1. I'll always get the outcome spin 1 along that axis. But for the mixed states, the expectation value is diminished. And we call that the polarization, since it characterizes the expectation value. If you think of it as a spin polarized or pointing in some direction. Now, as I've said, every mixed state of a qubit can be expressed as a convex combination of two pure states. And in fact, can be expressed that way in many ways. Well, actually, maybe I haven't said that yet. So what's the idea? Well, here we're talking about a qubit. All the possible states live in the ball. I can pick any point in the interior of the ball. And then if I want to consider any chord of the ball, any straight line that connects together 2 points on the boundary of the ball, if that line goes through this point in the interior, then that means that this density operator can be expressed as a convex combination of these two pure states which live on the boundary. Now, with the exception of the maximally mixed state, that's when the polarization is equal to 0. The density operator is just 1/2 the identity, and that's the point at the origin of the sphere. If I want to express the density operator as a convex combination of two mutually orthogonal pure states, there's a unique way of doing that. Because the pure states which are mutually orthogonal are the antipodal points on the sphere. That is, if I consider a line which goes through the center of the sphere, a diameter of the sphere, then the 2 points on the boundary that line intersects are pure states that are mutually orthogonal. Those correspond to, if we were to measure the spin along the axis picked out by that diameter, the 2 endpoints are the states which always are spin up or always are spin down when we measure along that direction, and those are mutually orthogonal. And we discussed that when we described the pure states of a qubit in the previous lecture. But there's nothing wrong with expressing this point in the interior as a convex combination of two states which are not mutually orthogonal. In other words, I can consider any chord, and if it goes through this point, the density operator I'm trying to describe, then where that line meets the boundary, those are pure states, and the appropriate convex combination with the right weight of the 2 endpoints, I'll hit this point. In other words, I'll have expressed that density operator as a convex combination of those 2 pure states, which are not mutually orthogonal. Now, another thing to note is that in the case of a qubit, in the case of a 2-dimensional Hilbert space, every state on the boundary of the space of density operators is a pure state. The space of density operators is the ball with unit radius in 3-dimensional space. The pure states are the sphere with unit radius, the boundary of the ball, and every point on that sphere is a pure state. In higher dimensions, the situation is different. In that case, we can have a density operator which is on the boundary of the space of possible density operators, but is not a pure state. I'll show you what I mean. by illustrating with the case of a three-dimensional Hilbert space. So consider some density operator for a system with a three-dimensional Hilbert space, expressed in terms of the projections onto the eigenvectors of the density operator. Let's call those eigenvectors 0, 1, and 2. Then there's some non-negative real number projection onto 0, plus non-negative real number projection onto 1, plus non-negative real number projection onto the state 2. That's what the density operator looks like in its diagonal basis. Now, if any one of those probabilities, P0, P1, P2, which sum up to 1, if any one of those is 0, that is on the boundary of the space of density operators, which are non-negative Hermitian operators. In other words, if let's say P0 is equal to 0, then there are matrices, 3 by 3 matrices, which are arbitrarily close by, which are not density operators, because they have eigenvalues which are just a little bit less than 0. But if I set P0 equal to 0, so I'm right on the boundary of the space of states, what I have is not in general a pure state. Rather, it's a convex combination of the state 1 and the state 2, unless either P1 or P2 is also 0. Okay, so the boundary is not the same as the set of pure states in dimension 3 or greater. Now, this idea of extremal points of probability distributions we can also discuss classically. And if I have a probability distribution in 3 dimensions, that is, if I want to consider probabilities assigned to 3 possible outcomes, let's call them P0 and P1 and P2, like I did here, then if I consider the space of all such probability distributions in 3 dimensions, there are 3 possible extremal points. We can visualize the geometry of that space of probability distributions as I've shown here with this triangle. Here I'm considering along the horizontal axis the value of the probability of outcome 0, and along the vertical axis the probability of the outcome 1. If both P0 and P1 are equal to 0, then that means P2 is equal to 1. So that is one of the extremal points where one of the outcomes, in that case the outcome 2, has probability 1. Okay. Up here, when P1 is equal to 1, well then, of course, P2 and P0 have to be equal to 0. So that's another extremal point where the outcome 1 occurs with probability 1. And then there's a third extremal point when here, where P0 is equal to 1, which means both P1 and P2 have to be equal to 0. Now, every other probability distribution governing those 3 possible outcomes, labeled 0, 1, and 2, can be expressed as a convex combination of those 3 extremal points. This vertex of the triangle, this one, and this one. All those possible convex combinations are all the points in the interior of the triangle, colored here in gray. So likewise, if I were considering d dimensions, the space of all possible probability distributions could be expressed as a convex combination of d extremal distributions, and in each one of the extremal distributions, one of the outcomes occurs with probability 1. Notice that in the quantum case, in the case of quantum states, quantum density operators, the geometry is different. And in fact, already in 2 dimensions, we see that although the Hilbert space is just 2-dimensional and the density operators have 3 real parameters, the extremal points are all the pure states. There are an infinite number of them. Every point on the unit sphere is an extremal point. Now, as I've said, if I want to express a density operator which is mixed as a convex combination of possible pure states, for any mixed state, there are many ways of doing that. Remember, we visualize that in the case of the qubit by noticing that this point in the boundary of the sphere could be expressed as either a convex combination of these two red points or a convex combination of these two, and there are many other possibilities as well, an infinite number. Let's be more general. Let's suppose we have a Hilbert space in some unspecified finite dimension, let's say d dimensions, and I can imagine expressing a density operator as a convex combination of pure states. Now, the number of pure states in that convex combination can be any number, even if the Hilbert space dimension is 3, say. There's nothing wrong with considering a convex combination of 18 possible density operators, or possible pure states to get a density operator. I could consult some probability distribution for 18 outcomes. I sample from it, and then prepare one of those 18 pure states to obtain the density operator. So here I haven't specified what I'm summing A over, but it's being summed over some finite number of values. And the density operator was obtained by, with probability PA, preparing a pure state, which I called phi A. So given a set of pure states and a corresponding probability distribution, that specifies an ensemble representation of a density operator. But that same density operator might instead be expressed as a convex combination of some other set of pure states. Now, these phi a's and these psi mu's don't have to be mutually orthogonal, as we saw here. I could consider this chord in the case of the Bloch sphere, which is not connecting two antipodal points, and so that describes a density operator in terms of an ensemble of states which are not mutually orthogonal. So I don't want to assume here that the states labeled psi mu or the states labeled phi a are necessarily orthogonal to one another. But what I would like to understand is, what can we say about the relationship between the state psi mu and the probability distribution q mu and the states phi a and the probability distribution PA, if both are ensemble representations of the same density operator? Now, if I'm given a density operator, there's something I can always do if I want to, and that is I can purify the density operator. This is a density operator just for Alice's system A, but let's suppose I imagine that although I only have access to system A, that there is some system B, and that the density operator for system A was actually obtained by taking a partial trace over that system B. Well, I can always construct such a pure state. In fact, if I want this density operator in which phi A occurs with probability PA, I can just consider this pure state of AB. I let the alpha A's be some orthonormal basis for system B. So I'm going to have to choose the dimension of system B to be large enough to have a dimension which is at least as large as the number of states phi A in the ensemble that I want to sample from. But if I introduce an orthonormal basis and assign a different element of that basis for system B to each one of the phi A's, I can construct this pure state for AB, and when I trace out system B, I'll just recover this density operator. I can just evaluate the trace using this alpha A basis, so that's easy to see. Well, likewise, for this other ensemble, in which I'm preparing the pure state psi sub mu with probability q sub mu, I could introduce some other orthonormal basis for system B and construct a pure state for AB, not necessarily the same one as phi A. I'm going to call this one phi 2. And by pairing up orthonormal basis states for Bob's system, B sub mu, with the state psi mu that I want to use in my convex combination to construct rho, if I now trace out system B, I will get this representation for the density operator. So if these are indeed two different ways of realizing the same density operator, there's some kind of relationship between phi 1 and phi 2 that we'd like to understand. But one way of thinking about this is that in the state phi1, we can imagine that Bob performs a measurement. He doesn't really have to do this. We can just trace him out. But suppose we imagine that Bob performs a measurement of system B in the alpha basis, and he does so when the bipartite state is the state phi1. Well, then he's going to get the outcome alpha A with probability PA. And when he gets the outcome alpha A, he will have prepared phi A. So that's just a way of realizing this ensemble representation of the density operator. We can imagine we have this bipartite pure state phi1, and Bob measures in the alpha basis, and then that means he's preparing phi A with probability PA. And on the other hand, if the bipartite pure state for A and B were phi2, now Bob can measure in the beta basis, and he'll get the outcome beta mu with probability Q mu. When he gets the outcome beta mu, he will have prepared psi mu for Alice's system. So that's a way of realizing the ensemble representation in terms of the pure state psi mu occurring with probability Q mu, another way of representing the same density operator, rho A. So now we'd like to ask, how are these two states, phi1 and phi2, related? And what I claim is that it's possible for Bob to turn the first state, phi1, into the second state, phi2, just by performing a unitary transformation on his system, on system B, without ever touching system A. So actually what that means is that there's a single purification of A, a pure state of system AB, such that Bob can measure in either one of two bases. And in one case, he'll be realizing the ensemble phi A with probability PA. And when he does the other measurement, he will be realizing the second ensemble, preparing psi mu with probability Q mu. Because if I can get one state from the other just by performing a unitary for Bob, all he has to do is perform that unitary first and then measure, and it'll be the same thing as the description I gave her here of measuring in the beta basis in the state phi1. So this statement that there's a single purification such that Bob can realize either of these ensemble representations by doing two alternative orthogonal measurements just on system B, this is called the Houston-Jozsa-Wooters theorem, or sometimes just the purification theorem. And the way to see it's true is to make use of the Schmidt decomposition. So we have these two states, remember, and we've been promised that if we trace out system B, we get the same density operator rho A if the shared state is phi1 or if the shared state is phi2. Now both phi1 and phi2 can be put in Schmidt form. I can choose orthonormal bases for systems A and B such that phi1 is in the Schmidt form. So it can be written as some other probability distribution given by the eigenvalues of the density operator rho A, lambda k. Of course, in the Schmidt decomposition, we have the square root of lambda k rather than lambda k itself. That's what will give us a normalized state, phi1. And then there's some orthonormal basis for Alice's system. I've called the elements of that basis k. And then there's some corresponding orthonormal basis in the Schmidt decomposition for Bob's system. And I'm calling those basis elements k1 prime, the 1, in reference to the fact that this is the state phi1. And I can do the same for phi2. Now, the lambda k's, remember, are just the eigenvalues of the density operator rho A. So those are going on microphone. Is it working? Yes, it's working fine. So let's get rid of that and assume everything's good. Okay, we're still recording. Remember that in the Schmidt form, this basis for Alice's system is just the basis in which the density operator is diagonal. So that's the same basis for phi1 and phi2 because they both have the same marginal density operator when we trace out B's system. So in order to get phi1 from phi2, all I have to do is rotate Bob's basis elements. I don't have to touch Alice's. I just have to rotate the K1 prime basis to the K2 prime basis. There's always some unitary transformation that does that rotates one unitary basis to the other. So phi1 can be written as identity on Alice's system. We don't touch Alice's system, tensored with some unitary on Bob's system, acting on phi2. Okay, and when we apply those unitaries to the basis that we use to express phi2 here, we just get some other basis. And I guess I decided to call that the gamma basis for system B. So now look at what we have here. We have a state phi1, which can be expressed in two ways. It's the same state expressed in two ways. And in the first way, if Bob measures in the alpha basis, he'll realize the first ensemble, phi A with probability PA. That's the alpha basis. And in the other basis, the gamma basis, if Bob does an orthogonal measurement in that basis, he'll be preparing psi mu with probability Q mu. Okay? And in fact, I could always take this gamma basis and I could re-express it in terms of the alpha basis by performing some unitary change of basis. So I can take this expression, which is just a way of writing phi1, and then use the expansion of the gamma mu's in terms of the alpha a's, and that's some other unitary operator, and I can think of it as a matrix with matrix elements VA mu. So I can write phi1 either this way, where if we measure in the alpha basis, we'll prepare the state phi A with probability PA. But here I've expressed it in terms of the alpha basis just by including the unitary that rotates the gamma basis to the alpha basis and including the matrix elements of the VA mu's. And so here we have two different expansions in terms of Bob's alpha basis, and they have to agree because they're two ways of expressing the same state. And we can see that what that means for each value of A, square root of PA times state vector phi A has to be the same thing as the sum of square root of Q mu, state vector psi mu, unitary matrix element VA mu. So if we have two different ensemble representations of the same density operator, they must be related in this way for some unitary matrix V. Now, when we do the sum over A and the sum over mu, those sums might have a different number of terms because the preparation in the phi basis and the preparation in the psi basis might have had a different number of possible states, but that's okay. We just choose the dimension of Bob's system to be sufficiently large as to accommodate the larger number of alternatives, whichever it is, between the phi basis and the psi basis. And then these are the matrix elements of a unitary where, well, I don't have to worry about others, which, because they're things that occur with zero probability. But there's going to be some unitary V, which is a square matrix whose dimension is determined by whether the number of values of mu or the number of values of A is larger, such that the two ensembles are related this way. And that's another way in which the HJW theorem is sometimes stated. Okay, so let's move on to measurements. We've been talking about density operators, but now I want to look at measurement as something more general than is encompassed by our measurement axiom for a closed system. So you can think of this as a kind of measurement in an open system, but let me motivate it in a somewhat different way. Usually when we do a measurement on a quantum system in the laboratory, the quantum system is some little itty bitty system. It doesn't have to be, but it could be an atom or it could be the spin of an electron or something like that. And it's hard to see that directly. So if we want to read out the outcome of a measurement on that, what do we usually do? We find some way of coupling the system that we want to measure, like the spin of the electron, to some other system that's easier for us to read out, some kind of meter or apparatus which we can look at. We can think of it as having a dial where the dial points to one of a set of possible numbers, and well, we can take it for granted that when we look at a dial, it's easy to see whether it's pointing to 1, 2, or 3, and so on. That's a lot easier than looking directly at the spin of the electron. So we can think of the measurement process as a two-step process. There's some quantum system, we want to measure it. So you could think of this as Alice and Bob again if you want to, and in fact, I will go back to that notation in a moment. But for now, I'm calling it S, the system that we want to measure, and A, the apparatus, which is the thing that's easy for us to look at. Never mind exactly how we look at it. We have some way of looking at this meter and seeing what it reads. So to do the measurement, first of all, we need S and A to interact with one another. We can start out in a state in which S and A are completely uncorrelated, in a product state of a state for S and a state for A. But then we turn on some interaction between S and A, and a unitary transformation occurs which acts collectively on S and A. And after that unitary transformation is complete, then we measure the apparatus. And when we do so, we will have prepared some state of the system, and we'll get some probability distribution for the outcomes of the measurement of the apparatus. And we can think of those as the probability of the outcomes for the measurement of the system, and the post-measurement state of the system is the state after our measurement is complete. So let's suppose that what we're interested in doing is performing an orthogonal measurement of the system, but we don't know how to do that directly. However, we do know how to do orthogonal measurements for the apparatus. So let's suppose that the different outcomes for the measurement of the system that we want to describe are labeled by orthogonal projectors. I've denoted them EA. Remember that what it means for them to be orthogonal, they're Hermitian operators, and they have the property that when A is not equal to B, EA, EB is equal to 0. On the other hand, EA squared is equal to EA. Now, EA is just the projection onto some subspace, and we'll also assume completeness that when we sum up all the possible projectors, we get the identity on the Hilbert space of the system. So that's what we'd like to measure. So how should we choose our unitary so that we can do our desired measurement on the system by measuring the apparatus? Well, we'll suppose that there's some corresponding orthonormal basis for the apparatus, and that somehow we know how to perform the orthogonal measurement on the apparatus, and we want to leverage that ability to perform the orthogonal measurement on the system. So I'll write the unitary this way, and you see we're summing over A, which labels the different alternatives for our measurement of the system. And corresponding in this sum to the projection EA acting on the system, there will be a shift in the basis for the apparatus. So the elements of the apparatus are labeled by A. Oh, wait a minute. I think maybe this isn't right. Hold on. Bear with me here for a second.